Hello everyone. Today let's solve the problem Appleman and the tree. Right. So this was asked in the Codeforces around 263 for the division 1. Sorry. Yeah, you can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So what the question states here. So just give me a second. 1 second, man. Yeah. Now Appleman has n node tree. Right. So Appleman, what is having? So I'll just write here. Appleman, nothing but AM I have considered that guy. Appleman has n node tree, right? Each node is black or white. So Appleman has n node tree and each node is either black, nothing but represented in the form of 1, the digit 1, or this one, white, nothing but represented in the form of 0. This is fine. Again, Appleman has n node tree. Each node is either black or white. So we have to choose any set of k edges, right? So we have to choose what we need to choose here. We need to choose any set of k edges to delete, right? So why we have to delete? Let's say the same thing. Let's discuss the same thing in the future, right? So choose any set k edges just to delete. So why we need to delete? So I'll just write delete here. So why we need to delete? Deleting k edges splits the tree into k plus 1 components, right? So deleting k edges splits the tree into k plus 1 component. So how this is helpful? Because we in the question we have been asked to count how many choices of edges make every resulting component contain exactly one black node. What we need to count here again? So this is how it is interlinked basically, right? If you think this is how this is interlinked basically, right? So now again, so what we need to count? We need to count how many choices of edges, how many chances of sorry, choices of edges or the vertices make every resulting component contain exactly one black node, right? Exactly one black node, right? So this is fine. Exactly one black node. Right? So this is fine. Again, let me read this one from the beginning. Just try to understand, right? So I've just summarized so that it will be easier for us to solve the problem. You can just go through the question and you can understand, in your own way, right? So this is the most summarized version, right? So this is on point, right? So whatever we need to calculate and whatever we have to do, that I'll just summarize and read it in the form of question. So I can just go through the question entirely if you don't understand this one, or listen to this again, right? So let me read out this one loud. So Appleman has n nodes again, n node tree, right? So each node is either black or white. We know this one. Black is represented by the digit 1 and white is represented by the digit 0, right? So we have to choose any set of k edges to delete, right? Again, one of the this one criteria they have given in the this thing constraints, k has to be greater than or equal to 0 and less than or equal to less than n, not equal to less than n. This is what they have mentioned in the constraints. So k has to be greater than or equal to 0 and less than n. Again, deleting k edges splits the tree into k plus 1 components, right? So what we need to do here, what is our main goal? We have to count how many choices of the edges make every resulting component contain exactly one black node, right? So that's what we need to count. Count, we have to count how many choices of edges make every resulting component contain exactly one black node. So we have to output the count mod in the sense, see here they have already given this is the value we have to, again, so this part is very important, so we have to use this mod value whenever they have given in the question, right? So we have to output the count put mod output the count mod. This one basically this is 10 to the power of 9 plus 7, that's what they have mentioned as well, right? So this one I wanted to say the same thing. This is nothing but 10 to the power of 9 plus 7. This is fine. Now I hope the question part is completely clear, man, right? Very simple to understand. They have given us input output part as well. Let's check what they have given here. Let's come to the first example here. Just give me a sec. Just give me a second here. Yeah. So see, we have been given here n equals 3, right? So we have been given n equals 3. 1 second. So why this is not working? Yeah. Now we have been given here n equals 3. This is fine. And 0 and 0 are nothing but the parents basically. These are the edges, right? So when I say parents, so this one parents, let me represent this one in the form of 0 and 0, right? So this edges I can represent in this way. Edges or the vertex I can just represent in this way: 0 to 1, and we have 0 to 2, right? So this is fine. Now colors we have been given, so this is nothing but the colors, and this part is nothing but the parent, right? So this is parent, this part is nothing but the colors basically, right? So we have been given 0 1 1 here, right? So node 0 is white. White is represented by 0 again. Black is represented by 1, right? So just give me a second, did I get confused here? Yeah, black is 1 and white is 0, right? Again, white is 0 and black is 1, right? So this is fine. Now we have node 0 white, node 1 this one, what do we call, black, and node 2 also black. So why I have considered here this one 0 to 1 and 1 to 2? Because we have from 0 to 2 nodes, we have from 0 to 2, so that is the reason edges I have considered from 0 to 1 and 0 to 2. 0 0 we have been given here, right? Parent. So this is fine. Now I hope this part is clear, man. Not to get confused here, right? So colors here, this one is 0 1 1, right? So colors we have been given 0 1 1, meaning node 0 we have, this is not no, this is node 0, right? So node 0 we have white, node 1 we have black, as well as node 2 we have black as well, because we have one digit 1, right? So again, node 2 is also black basically. Node 0 white, node 1 is black, and this one node 2 is also black. So the number of choices of edges that make every resulting component that contain exactly one black node is 2, 2 here in this case output. So how we got to, let's discuss the same thing in the approach, right? So let's consider the data structure, what we'll be using, and other stuff, what will be the main approach. So all these things we'll be discussing in the approach, right? So same goes with this input as well, man. Again, I'm gonna tell you. So I'll consider the example one for the this one, for this particular question, and I insist you to try out the same thing with the example two or the example three, so that you understand the question clearly. Let me delete this one, man, for now, right? So I hope the question part is completely clear along with the input output, right? So this is fine. Next, let's do one thing. Let's quickly discuss the complexities part, right? So let's quickly discuss the complexities part. Sorry, not the complexities, approach part, right? So just give me a second here. So I have considered the same first example here. So we have n equals 3. We have already discussed this one. Basically, this is nothing but the parent. So it just here 0 to 1 and 0 to 2. So because we have two nodes here, and again, don't get confused here. Indexing start from the 0 for the trees. When we are considering trees, this is nothing but the tree based, right? So this is the tree question basically, based on the tree. So indexing starts from the 0. So this is we don't call this one, actually we have three nodes, we have two nodes, right? 0 1 2. So indexing starts from 0 again, don't get confused here. This is 0 1 1. So 0 1 1 node 0 is this one white basically. Node 1 we have black, and node 2 also we have black. We have discussed this one, this is fine. Output that we need to get here is 2. So one more thing, we'll be making use of the dynamic programming to solve this particular problem, right? So this is nothing but the DP on trees, man, right? So we'll be going with the dynamic programming for this particular problem. Let's move on with the step-by-step explanation. Same thing I have said here. N equals 3, parents adjust, this is fine. Colors 0 1 1, node 0, this is fine, man. We have already discussed this one. So let's move on with the further this thing, for the this one, what do we call, further things. So this is fine, we do DP on the tree. So we will be doing the dynamic programming, we'll be implementing the DP on the tree basically, right? For each node u, we will maintain DP of u0 and DP of u1 in the sense. So I have written the same thing, don't get confused here. DP of u0 is nothing but the number of ways inside u subtree, so that component that contains u has 0 black nodes, right? Number of ways inside u subtree, so that component that contains u has this one 0 black nodes. And what about DP of u1? Number of ways inside use again subtree, so that the component that contains has exactly one black, exactly one black, here exactly zero black, here exactly one black, right? So this is fine. Exact in the sense this one, zero black nodes, not exact. So zero means zero, right? So this one exactly has one black node. So this is fine. Now this is what you need to understand. We are doing DP on tree basically, or we are implementing DP on that tree. For each node we are going to maintain, or we'll be maintaining this one, DP of u0 and DP of u1. So we know this one, I have already explained this one. Next, let's move on with the next steps. So first we are going with a base at node. This is before merging the children. This is the merging children part. So this is before merging children. Nothing but you can just call this one equivalent to the initialization part as well, right? So if node is white, then we will be going with dp of u equals 1 comma 0, right? So just keep this in mind. If node is white, then we'll be going with dp of u equals 1 comma 0, and if black, same thing, we'll reverse this one, right? So we'll go with 0 comma 1. So this is nothing but the base at node, right? So this is nothing but base at node, right? So this is fine, I believe, right? So here, when I say if node is white, dp of u equals 1 comma 0, whatever we are considering, this is nothing but its own component has zero black infinity, right? Its own component has zero black infinity, right? So here, for the black, its own component has one black, exact one black. So this we can derive from this part, right? So I have already explained this one. So we are implementing DP on trees. For each node u, we are maintaining DP of u0, DP of u1. u0 is nothing but number of ways inside u subtree, so that the component that contains u has zero black nodes. For this one, same thing, but it can component, this one that contains has that contains u has exactly one black. So from this itself we are deriving to this one, right? So just give me a second here, this one. So now if node is white, dp of u is 1 comma 0, meaning its own component has zero black initially. Sorry man, this one is not infinity. Did I say infinity? So sorry, this one is not infinity, this one is initially. Sorry, why did I say infinity? This is fine. If node is white, so this is 0 and 1. Why did I say infinity? This is fine. Its own component has black initially, and this one, its own component has one black, right? So you know how it how we have written this one. This is fine. Now let's move on with the next part, nothing but the merge child v into parent u. So we have to merge child v into parent u, right? So now this one, I have shown this one in the form of code basically. So dp of u0 is old 0 into dp of v0 plus dp of v1, right? So this is fine. New dp of u1 is equivalent to this one, old 1 into same thing, instead of the old 0 we are going with old 1 here. Dp of v0 remains same, plus dp of v1, this remains same. Along with that, we will be going with plus old 0 into dp of v1, right? For the new dp, for the new dp. So this is for the merge. We are just merging the child v into the parent u. Just try to remember this one, right? So this is fine, man. Now what we are gonna do, so let's apply this one to the example, right? So let's try to apply this one to the example. Now let's do one thing. Let's go with the node 1. So we have 0 1 and 2, right? So we have two nodes basically in simple terms. So let's apply to the example, right? So now we have node 1, nothing but initially black, right? So node 1, nothing but black. So here dp of 1 is nothing but, we have for the black we have 0 1, right? For the black we have 0 1, for the white we have 1 0. So we have already discussed this one, you should be knowing this one, right? So dp of 1, again node 2 we have black, node 0 is having white, node 1 and 2 we have black. For the black we are going with 0 comma 1, and for the white we are going with 1 comma 0. This one initialization dp of 1 0 1 0 1 and 1 0. Now let's merge the child one. So with this formula, this one, this one, right? This one, we are merging child v into the parent v basically, right? So one second, did I write v here? This is u, man, not v. Sorry, got confused. We are merging the child v into the parent u basically, not v. So this is fine. we will be merging the child one, meaning dp of 0 will be going with 1 into 0 plus 1. This is nothing but 1. Here 0 into 0 plus 1 plus 1 into 1. This is equivalent to 1, right? So now dp of 0 is nothing but here 1 comma 1. Just give me a second here. So this is fine. Now we are just going with the same formula. So this is nothing but, so here see, my child dp of u, this one old 0, this one, this formula itself we are going with, right? So we have to go with this one new, this one, right? So this one. So this is fine. Now this will be 1 into 0 plus 1. This one, when we do the calculation, this will be basically 1. So this will be 1 comma 1, right? So this will be 1 into 0 plus 1. This will be equivalent to 1. And this one will be 0 into 0 plus 1. 0 into something is 0. And plus 1 into 1 will lead to 1 itself. So dp of 0 is nothing but 1 comma 1 we got here, right? So we have to merge the child 2 as well. Child 1 and child 2 we have to merge, right? So this one, the same formula will be applying here, this one. So this we will be getting 1 comma 2. First we have got 1 comma 1, I believe. Next we got 1 comma 2, right? So 1 comma 1 and 1 comma 2, totally we got 2, right? So answer is nothing but here, in the sense answer is dp of root 1 is nothing but 2. We have got dp of 0 equals 1 comma 1 and dp of 0 equals 1 comma 2 here in this case, right? So this is nothing but, there are two valid edge sets, right? There are two valid edge sets, right? So cut at 0 to 1, or cut 0 to 2 only, right? In the sense, so we can just go with a cut at 0 to 1 only, or cut 0 to 2 only, right? So basically dp of root 1 is 2 here, right? So dp of root 1 is 2 here. This is fine. So the output that we need to get here is this one. The output that we got here is 2, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So our approach works absolutely correct in this case. Our approach works absolutely correct in this case. As we are completely familiar with the approach, let's discuss the complexities part. So what will be the time complexity and the space complexity here? The time complexity would be big of n, and the space complexity would be big of n as well. So why the time complexity here is big of n? Because each edge, right? So here each edge or node, right? So each edge or node is visited once, and every merge is constant time per child. So overall time complexity would quite obviously lead to big of n. So what about the space complexity here? The space complexity is big of n as well, because we'll be going with the adjacency list for the this one graph, and this one dp arrays also, as we are going with the dp. So we'll be going with the dp arrays and the recursion stack that would lead to verse of this one big often, we know this, right? Recursion stack, in the sense we'll be making use of the dfs, just remember this one. So we'll be going with a recursive dfs, right? So this is fine. Now we'll be going with the adjacency list, dp arrays, as well as the recursion stack, this one, because of the DFS that requires linear space, nothing but big of n in this case, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively, right? So I hope this part is completely clear, man. Uh, just give me a second here. 1 second. Yep. This is fine, man. Now, now as we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come to the compiler. So we'll be making use of the fast input output. So let me import input output package first. So I'll just go with input output dot star. This is fine. Let me import utilities different. I will be making use of the different utilities. So let's import utility package as well. Right, so this is fine. Now let's go with some class. So I'll just go with a class main. So this is fine. So I can just give any name that is relevant to the question. So I'll just give main here. So first of all, they have asked in the question to make use of the mod value, right? So let's go with the modulus for answers as it is asked in the question. So I'll just go with the static here. So this one final. So int, let me go with the variable mod here. So they have given 10 to the power of 9 plus 7, right? So in the question, Just give me a second here. Yep. Uh, this one. Let me go with here. Can just either write it like this, or I'll just go with here, so that this is fine. Yep, this is modulus for the answers as required. Now let me go with the, so we have to go with the adjacency list for the tree. So for that, let me consider here static list of what, integers, right? So I'll just go with the integer here. So variable name I'll consider here g. This is fine. Now uh, let's go with the column. Uh, Column, not the column, basically color array. So when I say color array, uh, if it is true if black, false if white, right? So color array, it is true if black, false if white, right? So I'll just go with the static here. This is fine. Let me go with boolean uh, column, this one, colors, not the column one. So this is nothing but the color array. Color array 0 1 1 we have given in the input month, that is the color array we have to consider. So this one I'm speaking of. Why am I getting color in the this one in my mind? I don't know. So this is nothing but the color array. Next we have to mark the visited, right? We'll be making use of the DFS, as I've said. We'll be going with the helper method DFS. So we have to go with a visited marker for the DFS, nothing but I'll just go with visited. So let me write it on this way. Static, again boolean. So this one, let me go with visited. BIS is enough. So let me go with static one more type. So this one will be long. So this time we'll be going with the DP. So nothing but DP array. DP of u and 0 or 1, right? So we'll be going with DP of u, one thing, and in the other array we'll be either considering 0 or 1, right? So this one we have already discussed in the approach, man. Final one, we have to go with the number of nodes, right? So let me initialize n, variable n here, which is of the type integer. So this is fine. We're done with the initialization part. Next, let's move on with the main method. So let me remove this one. So here, let me consider throws input output exception, or else if we don't give this, we'll get the error, right? So this is fine. Now for the input output, let me make use of buffered reader. So this is fine. Br, this one is equivalent to new buffered reader, new input stream reader. So this one system dot n. This is fine. So now we have to read the number of vertices, meaning here n equals integer dot percent. So this one is fine, percent. So this one will be PR buffered reader dot read line, right? So buffered reader dot read line, this is fine. Now we have to initialize the adjacency lists, nothing but g equals new array list of this one n. This is fine. Yep. So let's go with a simple for loop here. For so this one will be int I equals 0, I less than n. So this will be I plus plus. So iterated value of the g. So let me assign this one to new array list. Yeah, this is fine. Next, we have initialized the adjacency list. So this part is completed. Now, if you remember in the approach, we have to read the parent array, nothing but n minus 1 integers, right? So here, let's go with a pi, meaning pi. I'm speaking of pi, meaning edge between I plus 1 and pi, right? So let's see. Let's try to implement same thing in the form of code. Let me make use of string tokenizer here. This is fine. St string tokenizer equivalent to new string tokenizer. Let me pass buffered reader dot read line. Yep. Now let's move on with the iteration part. So this one will be int I equals 0, I less than n. So this one will be I plus plus. So within the for loop, let me go with p here. This one integer dot percent. So this is fine. String tokenizer dot, this one will be next token, right? So I'll just go with next token. This is fine. Yep. Now let's go with the undirected edges, meaning so we have to connect parent p and child I plus 1, if you remember the approach, right? So this one will be g of p. G is nothing but here we have considered g, right? So this one. So basically what is g? G is nothing but the adjacency list for the tree. We know this one, right? So now we are going with the undirected edges, meaning we are connecting the parent p and the child I plus 1. So this one is g of p. So let me make use of the add property here. We are connecting, right? So I plus 1. This is fine. Next, g of I plus 1. So this one, what we have to add this time? P. This is fine. Now we are done with this. Let me come out of this one entirely. Now, after doing this, so we have to read the colors, right? So xi here, in simple terms, it is 1. If it is 1, then it is black. If it is 0, then it is white. I'll be considering this one. Basically, nothing. So just leave it here. Let me leave it here. So just try to understand this. We are reading the colors now. So I'll just go with the color. This one equals new. Let me go with boolean here. So let me pass n. This is fine. Now let me go with string tokenizer here. New string tokenizer. This one buffered reader dot read line. So this is also fine. Now let me go with for loop. So int I equals 0, I less than n. So this one, let me go with I plus plus. So this is nothing but iterated value of the column. So string tokenizer dot next token. This is also fine. Then let's go with the equals here. So this one and this will be 1. This is fine. Yup. Now let's go with the DP and the visited arrays. So DP is nothing but here new long of, so this one will be n and this one will be 2. This is fine. Also we have to go with the visited arrays as well, right? I have considered, or I have initialized with vis, I believe. Yeah, this is fine. Vis equals, so this is of type boolean, right? So I've initialized with a boolean, type boolean. So this one, let me pass n here. So this is fine, man. Now let's try to run the DFS from node 0. Before uh, we are trying to run DFS directly, right? So we have not written the DFS helper method at all. Let's write that one first, and then let's come to the main method here. So I'll just go with, just give me a second here, 1 second. Yeah, so let me go with the DFS helper method here. So I'll just go with static. So this one void. So let me go with DFS. The parameter that I need is u only, right? So this is nothing but the DFS that fills DP of u0 and DP of u1, right? For the subtree rooted at u, as we had discussed on the approach. So now don't get confused within this method. Let's mark the current node visited first. So this one visited of u. So this one, let's assign this one to true. And the next one is we have to initialize the DP for node alone, as well as if the node is black, its component currently has one black, else it has 0. This we know from the approach. This I had stressed this one multiple times, right? So let's try to implement the same thing in the form of code. So this is fine. So this one is dp of u0 column u. Let me make use of the ternary operator here. This will be actually, this works actually if I make use of the ternary operator. It will be 0, else it is 1. In the sense, we are initializing the DP for node alone. If the node is black, its component currently has one black, else it has 0, right? So that's what. The same thing, let's do it for the DP of U1 as well. So I'll just, sorry, let me copy the entire thing. So let me come to the next line. Let me paste it over here. So this one will be DP of U1. So column U, this is fine, 0, 1. This one has to be here 1, else 0. This is fine. Now, right, so this is fine. Now what we need to do, we have to iterate children, right? So when I say we have to iterate children, meaning neighbors that are not visited, right? So we have to iterate through the children, meaning the neighbors who are not visited or that are not visited, right? So this one, let me write for here int v. So this one of graph of this one u, so this is fine. If not of visited of v, this is fine. Now let me go with dfs of v, this is fine. Now we are done with this part. We are just computing dp for the child v. So now let's do one thing. We have to store the old values, right? Meaning we have to store the old values before merging v, right? So before the merging part we have to store the old values, right, accordingly with the approach. So I'll just go with long a0 here. So let it be dp of u0 comma a1. This is nothing but dp of u and 1. This is also fine. Let me do one thing. Let's go with dp of u and dp of 1, the formula that I mentioned. First one we considered base, right? So next we went with merging of the children, those two steps. If you remember the approach, you can just go back in the video and you can just see that within the approach and you can come back, right? So if you didn't understand, so the same thing I'll be writing here. So this one will be dp of u0. This will be, as I have considered a0, this will be a0 into dp of v0, uh, v and 0, sorry, not v0, 0 plus dp of v1. This is also fine, modulo mod. This is fine. Now else we'll be going with a dp of u1. So this one will be a1 into dp of v. This one will be 0 plus dp of dp of v0 we have given, right? So dp of v, this one will be 1. This is fine. uh, Again we have to go with a0, if you remember, right? So this one a0 into, I have considered the different variable name, that's it, right? So this is a0 I have considered here, a0 into dp of v1. This is the formula we went with, right? So this is dp of v1. This one modulo mod. This is fine. Now we are done with this part, man. Yep, we are done with this part. Meaning we are done with the helper method DFS. Now let's do one thing. Let's try to implement the same thing in the main method, right? So let's run the DFS from the node 0, right? So meaning tree is connected, any node would do. If the tree is connected, then any node would do, right? So we have to just run the DFS from node 0. So let me give here DFS of 0, as we are starting from the node 0. This is fine. Now we are left with only one thing, meaning we have to display the final answer, or we have to go with the final answer, right? Number of ways to split the whole tree so that roots component exactly has one black node, right? So that's what they have asked in the question, right, to do basically. So let me make use of the this one, system out parental. So we can just go sorry here, right? So we can just go with a out dot print as well, as you have made use of the double. Let me go with system out parental. So let me go with here system out print is enough, I believe. We have got on, we should get only one answer, and that one we have to print in the same line, right? So this is fine. So ln is required. Just give me a second here. Yeah, let me go with ln here. Let's check. So this is fine. Now let me go with dp of 0, 1. So this one modulo mod. So this is fine. Now yeah, we are done. We are done with the coding part basically, right? So we are done with the coding part. So let's do one thing. I'll just come here. Let me copy this one. Before doing this, let me tell you one thing. Before checking the code with different inputs, so let me copy paste the signature starter template one. Just give me a second here. So I'll just come here. Let me paste this one. Now let me come to the question. Let me copy this one input and let's check. So let me run this one. I believe we have the error, man. What error we have? One warning we have. So this is not showing the output at all, man. So what if I Copy this one, paste it over here. This is not showing the output at all. This is just showing the warning. Let's do one thing. Let me copy this one entirely and let me paste this one directly. Just guessing this would work. I don't know. In the compiler, it's just showing here this one. And I am just believing I have written the code correctly. Let's see. If something goes wrong, then we can come back and just check again, right? So if this works, let's not touch it. Let's wait for some time. So went with this one B, right? 461B, Appleman and the tree. So let's wait for some time. What happened to this one? Oh, this is showing runtime error on test one. What's wrong here? Let's check what is wrong. So what mistake I have done here is, so in the line number 37, instead of I less than n, I have to give I less than n minus 1. Accordingly, with the problem, they have mentioned from 0 to n minus 1. So we have to consider from up to n minus 1 edges, right? So we have to go with n minus 1 rather than n here, right? So I hope this works now. Let's see. So yeah, we are getting the output 1. We have, oh, I have considered second example, right? So yeah, this is working correctly. So I thought I had considered first example. Now let me do one thing. Let me run this one. We have to get output 2. Yeah, we are getting correct output. Now let me go with the final one. We have to get output 27. Let's see. Yeah, now this is working correctly, right? So let's ignore this warning one. This is fine. Let me remove this one. Let me paste this one over here and hit the submit button. Now this has to work, I believe. Right, so this has worked for all the three examples that they've given in the question. Let's see whether this works for all the test cases or not. Let's wait for some time. This was for the previous one, I believe. Yeah, let's wait for some time, man. So this is running on test 5. Yep, 11. Yep, let's wait for some time. So here you can clearly see the verdict that we got here is accepted. Means whatever the code that we have written works absolutely correct for all the test cases, right? So we have made use of DP along with the DFS here. We are applying the DP on the trees basically in simple terms, right? So strictly we are applying the DP on trees here, right? So we are performing the DFS along with the DP on trees. Simple, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.